Hello guys, how you doing? I'm Rahul and you're watching the Concept Builder. And today guys, we're gonna cover a new topic of our distillation series, and the topic today is called as batch distillation, also called as differential distillation and also called as simple distillation. So without wasting any time, let's get started. Okay, so as the name suggests, it is a batch distillation column or a batch distillation operation. So what we're gonna do that we're gonna use a still pot in which we're gonna charge our feed at once. Okay, and after that we're gonna close this vessel and we're gonna start heating it until the mixture starts boiling. Okay, and for heating we can use steam jacket or some kind of electric furnace also. Okay, so by any means we're gonna heat the mixture until it starts boiling. Okay, and as it starts boiling, it will produce vapor, and the vapor will be in equilibrium with the liquid if we are slow enough. And that is our basic assumption in this, that in ideal batch operation the vapor produced will be in equilibrium with the liquid. Okay, so what we're gonna do now, just the vapor will keep producing, and the vapor we're gonna take out from the top and we're gonna condense it, hold the vapor, we're gonna condense it and we're gonna collect it, and it will be our product. So it's very simple. Okay, and now one more thing I want to ask you, that can you imagine that what will be its effect on our txy diagram, like what will happen on our txy diagram that we studied it in our first distillation video. So just think about it and try to draw like what happens on the txy diagram. And now what we're gonna do is we're gonna apply our material balance so that we can see like how to relate the product purity with the, you know, the amount of feed left. Okay, like that. So you already know that how we're gonna do it. So first we're gonna do the overall balance, then we're gonna do the component balance, and so in this case there is some little change. We're gonna do the overall balance, but it's gonna be a differential material balance, and also it's gonna be a differential component balance. So what's the mean of differential is that we're gonna apply it on a small amount, like a differential amount of the feed and all that. So let's see how we're gonna do it. Okay, so in the equation, the first equation we're gonna make is minus dl equal to dd. Okay, so let me just clear it, that the l is over here is the amount of feed, amount of feed as a liquid, okay, in the still pot, and the capital D is the amount of vapor produced. Okay, it's clear. So at any time if you see that if dl amount of liquid is vaporized, okay, so if dl amount of liquid is changed, then the dd amount of vapor will be produced. Okay, because the liquid is ultimately getting into vapor, and it's very simple, and both gonna be equal, and we're gonna using the negative sign because the amount of liquid is decreasing, so dl will be negative. Okay, so it's gonna be our first material balance, the first overall differential material balance, and from this we can also do the material balance on the component A, which is our more volatile component. But here's the trick, that as I already told you, that the vapor producing it in the equilibrium with the liquid. So the value of y, the mole fraction in the vapor, will be related to the amount in the liquid, which is x. So the y will be equal to mx, like that. Okay, so they will give you some relationship, there will be some relationship according to the equilibrium, and we will have always the relation between y and the x, and y here is the vapor composition, and here as it is in equilibrium with the x, we're gonna call it y star. So when we use y star, that means the device is in equilibrium with the x. Okay, so let's do the component balance. So we're gonna write it like this. Okay, it's very simple. So just after some simple modification and using both the terms, okay, you can do it as your homework. It's very simple, just a little use of our differentiation, a little use of mathematics, that's all. And if you rearrange it and all that, you will get the formula, and the formula is very important. So what this formula is all about, that you can see that it is an integration kind of formula. So you have ln f by w equal to like kind of integration from xw. So xw is the final composition of the feed left as a liquid, okay, and the upper limit is xf, which is the mole fraction of initial feed. So here you can see that we did not talk about the product purity over here, okay, so that's very important. We're gonna talk about only the liquid left and the feed initially we charged. So f here is the feed initially we charged, okay, and the w is the feed left after the distillation over, okay. So it's the feed left is w and the feed charge is f, and xw and xf are their mole fractions, okay. And if you see the integration term, that it is dx divided by y star minus x, and I already told you that they will give you some equation of y star with x. So you have to put this value of y star from the given equation, and all integration will be in terms of x, and you have to just integrate it, and in most of the times it will be kind of like ln x and all that, and put the limits and solve it, and you will get your answer. So what you will get is that you will get the amount of w and f and all that. But what if they ask about the product purity? What if they said that what will be the purity of the product? Then from this equation we cannot get the product purity. And here comes the one more important concept, like what we're gonna do if they ask like that. Okay, so this is very important. You should note down that in this case, if they ask about the product purity, we're gonna use the our material balance that we gonna use, that we used in our flash distillation and all that. So f equal to d plus w, that's we're gonna use, and also the component balance you can use, and using both of these you can get the product purity.